The second type of NMR is carbon-13 NMR. So let's talk about this. It's not as long as the proton, but it's still significant. So first of all, a little bit about the introduction and theory. So I'm going to read through some of these points and explain them to you. So first of all, carbon, okay, by itself as an atom. So carbon 12 actually has no magnetic spin. It is diamagnetic because the 12 that tells you that the particles in the nucleus are paired up. So if they're all paired, then it's not going to have any activity in the magnetic spectrum, okay, or the magnetic field. So carbon 12 does not show up, okay, in the NMR. That's why this is carbon 13, because carbon 13, an isotope of carbon, has a magnetic spin. Odd number, right? So you should have odd number of particles in the nucleus. But the thing is, there's only 1% of carbon-13 in carbon isotopes that are naturally occurring. And so this is a little bit hard to see, but in NMR we can see carbon-13. So you just need a little bit more time and you need a little bit more sample, but you can take, okay, you can do carbon-13 NMR. You use the same instrumentation, you just have a different probe, okay, for it. Probe means sample holder, okay, for it, but otherwise you can do carbon-13 in the same NMR. Generally, there is no coupling because it's very hard to find a carbon-13 next to a carbon-13. Remember, coupling is a neighboring property. So you have to have two of the same particles next to each other. So generally carbon-13, there's not another one next to it. So every signal that you see is going to be a singlet. Okay, so just a single peak. And sometimes even if there is coupling, the instrumentation is done in such a way that decoupling is done. Okay, so you don't really see any coupling going on even within carbon and hydrogen sometimes. So that kind of avoids all sorts of problems, okay, in that case. The chemical shift scale is going to be a little bit different. It's still in ppm, okay, because you're still working with the ratio, but the scale is going to be from 0 ppm to 230 ppm, okay, so a little bit higher. Obviously you can tell 0 to 12 was proton, and so this is very high frequency, okay, that we're looking on. We don't really do integration as deeply as we do for proton NMR, but intensity of a signal can still give you a little bit of an idea of how many carbons are under that peak. So which means you can still calculate integration, okay, a little bit. Generally, the number of peaks that you see in the sample in the graph will tell you how many carbons there are. Just remember again, if you have equivalent carbons, they're going to show up as 1, right? Because if you have equivalent types of atoms, they show up only as 1 signal. So keeping that in mind, if you have 10 carbons, if you have 10 signals, it means you have 10 different kinds of carbons, okay? Now the intensity will tell you how many carbons you have under that peak, all right? But other than that, 10 peaks means 10 carbons, okay? At least you have that much. There are some other techniques that we use in carbon-13 that can help us a little bit, and one of the most important one is depth. You can read this all yourself. And what depth does for us is it separates out the carbon into primary, secondary, tertiary, and quaternary, which is a great help, okay? Because if you're looking at all singlets, then you don't really know what carbons we are talking about, right? So just separating out into primary, secondary, tertiary helps a lot, okay? Because at least you know then how many hydrogens are attached to that carbon. The other most important thing we can do with carbon-13 is we can correlate the spectrum with a proton NMR, which gives us what is called a het-core spectrum, and that heterocorrelation then it's the most beautiful thing. You can associate every hydrogen to carbons. Okay, so I'll show you a spectrum for that also, but there's a lot of fun things you can do with carbon-13 and proton. Okay, if you just give it a little time, you can find it a lot. Okay, so this is kind of like the basics of the carbon-13. The theory I'm not going to go over that much again because it's the same thing as proton, that you have a magnetic field and the radio frequency is going to help resonate the nuclei. Okay, So here is the spectrum for 2-butanone, okay, and you can see very simple, straightforward, singles, peaks. You still have the TMS, right, that you have to put for reference point for 0 ppm. Other than that, everything else is a single, okay. So here you have 2-butanone structure, so you have 4 carbons and you have 4 peaks, okay, because each of those carbons is different, okay. Look at the chemical shift, 0 to 200, and actually it's actually 210 because this peak is coming at 208, okay. So we're going to go through the carbon 13 NMR just like we did with the proton NMR. We'll start with the number of signals. All right, so how many signals do you see for any compound right here? So I have drawn this in a way where, you see all the hydrogens, and that's because, I still have the same compounds as before, but you can draw the, line structure out so you don't have to worry about all the hydrogens in there. So again, look for symmetry in the molecule, okay? And so here the symmetry is going to be like this. So which means 1, 2, 1, 2, right? So you have 2 signals that you're going to see for butane. For ethane, it's going to be just the 1 peak. For cyclohexane, remember, 1 peak, okay? It was the same for proton. It's the same thing going to be for carbon also because all the carbons are alike. And again, you can draw the symmetry if you want, and so every line is being crossed, and so therefore you only have 1 signal. For the next one here, if you want, again, let's go ahead and draw the line structure, okay, for this one. So again, these 2 carbons are going to be the same. This is separate. So 1, 2, 3, 4. Okay, so you end up seeing 4 peaks for that compound for 2-methyl butane. Now the next one here, remember this was like this, and if you don't remember, here it is, okay, 1,2-dimethyl cyclopentane. And so in this case, again, go ahead and draw the symmetrical line, which I have here in the curved line, but draw the line here. So then just count every carbon separating that line, okay. And so 1, 2, 3, 4. That's how it is, okay. And then so this one is easy enough to do, 1, 2, and then this is 1, 2. The next one is also easy to do. I just want to do the last one here with you because what happens is that sometimes when we look at compounds like these ones, we say, oh, 1, 2, 1, 2, but don't forget 3. Okay, so 3 peaks over here. So carbon with the carbonyl is also going to show up. Okay, so don't get sidetracked by looking at the hydrogens. Don't forget that you're looking at carbons and not hydrogens when you look at carbon 13. So count any number of carbons you might have in there. Okay, so even if you have esters, or ketones, you have to count everything. So 1, 2, 3, 4, 5. Okay, that's how many it's going to have. So anyhow, just kind of wanted to remind you of that you don't forget that this is carbon and not proton. Okay, so you count the carbonyl carbon as well. So now for the chemical shifts, okay, so we talked about the number of signals. The chemical shift is very similar to proton, okay? So if you remember, we talked about the alkanes. This is a proton one on the top, okay? Alkanes come over here. Here is the aromatic, aldehyde, and acids is the same thing. Alkanes come over here, and then aromatics are here, and then carbonyls are here. Remember, there is no acid because that's carbonyl. All right, so that's going to be around 200. Now the thing that you need to remember for chemical shifts here is the downfield and the upfield. Okay, just like here for protons you have the upfield and downfield, it's the same thing here. So there's no point remembering actual numbers, okay, for it. So maybe if you can remember 150 for aromatic and 200 for carbonyl, maybe that should be good enough, okay, for it. Alkanes are always going to be over here. So the other things in the middle, it's hard for you to remember. I don't want you to, put your memory to test for that. There are other things to remember. Also because, you add chlorine, bromine, and that chemical shift is going to change depending on how electronegative that element is. Okay, so just remember a few things and that should be sufficient. Okay, but I will ask you to do the upfield and the downfield for carbon 13 as well. So here is an example of that. Okay, so if you had, let's say, acetic acid, I have circled already the carbons that are going to be the most downfield, because then you just look at the carbon that's attached to electronegative elements. Okay, that's going to be the most downfield shifted carbon of all. So here this carbon is going to be the most downfield, the one connected to chlorine here, that's going to be the most downfield. Between this carbon and this carbon on an ether, the one on the right is going to be more downfield because this one has two carbons attached to it. So this one should be more downfield. And then in case of the alcohol, this carbon should be the most downfield. Now in this case, don't forget, this is highly symmetrical molecule. Okay, so first of all, I mean, if you want to do this, we can, is how many signals you will see for this would be 1 and 2. Okay, so just kind of give yourself a symmetrical line over here. So 1 and 2. Okay, that's in the quadrant. So those are the two signals you will see. And so which means that, let me erase all of this, is that this carbon and this carbon, okay, they are exactly the same. So that between those two signals, the circled ones will be then the downfield shifted, okay, in there. So that's how you will do for carbon 13 NMR for downfield shifting. So here is an example of a depth for carbon 13. So as I said, you know, you can kind of look at the structure and see, okay, you know, how many CH3s I have, CH2, CH. So this is the structure for 1-chloro. This is the NMR4, 1-chloro, 2-propanol. So if you want to draw it out, let's go ahead and do that. So it's a propanol, 2-propanol, 1-chloro, 2-propanol. So you have a CH3 here, you have a CH here and a CH2, right? So this is 2 hydrogens here. So which means that you have a peak here for CH3, you have a peak for CH2 and a peak for CH, which we're showing all here as 3 different peaks. So now you can separate them out, okay, and then you can assign that, all right. And so I mean, yeah, the NMR will assign, the computer will assign that for you as to which one is the CH3 peak, which one is the CH peak. So you know, it kind of becomes a lot easier to then start analyzing your carbon 13 NMR, because you can actually see which carbon is the most downfield shifted and which one has more hydrogens. So anyway, it helps. And then here is a combined spectrum for carbon and hydrogen. Yes, that is also possible. So here is the proton. Just look at the scale here. Okay, so this is the proton NMR, and then here's the carbon 13 NMR. Okay, so this one is for this kind of a pyrrole compound. And so in this pyrrole compound, look, you have an aldehyde. Now we didn't see this in the proton NMR. Okay, but the proton chemical shift for an aldehyde is going to be around 9 ppm. So there it is. And then the carbonyl is also around here. So, you know, you can kind of correlate a little bit and say, oh, okay, I have something that is very downfield shifted, right? So that will help a little bit. This is all aromatic. Okay, so pyrrole is an aromatic compound. So aromatic protons are going to show up around 7, just like benzene will. So, you know, you can kind of help yourself a little bit if you have the two spectrum right next to each other, and the computer can do this for you. Okay, you run both of these spectra together, well, one by one, and then once you have them together, then you can kind of manipulate that a little bit. And then here's a het core. Okay, and a het core would be where you have a carbon and the proton NMR kind of in one dimension, and the other dimension is for carbon. So, you know, in each dimension, and then you can correlate each peak to, remember I was telling you that this is kind of like a GIS system where you're flying over a mountain range. So here is your mountain range, and then all you look at is the longitude and latitude, and then kind of correlate, oh, okay, this proton belongs to this carbon, this proton belongs to this carbon. So, you know, for complex structures, it becomes a really then very useful technique. Okay, simple compounds you can figure out. Okay, but for something that's very complex and the splitting is very complex, you do 2D NMR, and then you can do the het core to figure out exactly which carbon belongs to which proton. So it's very helpful. So spin splitting, just want to remind you again that there is no splitting, okay, in carbon 13, because the next thing we would have done is talked about coupling and all that, but there is no spin splitting, okay. So that's kind of makes it a little bit easier for us to, easy, or at least we know there's no coupling, okay. They're only going to be singlets in there. So interpreting a carbon 13 NMR, you kind of just have to um, I wouldn't say take a guess, for things, because you can take definitely a very good educated guess and come up with structures. But at least, if you have 5 signals in the NMR, then you know that you have 5 different kind of carbons. And then you look at the location. So that gives you an idea of, okay, I have something downfield shifted or aromatic. And then you can look at the peak area to tell you, if you have more carbons in there, okay? Because just because you have 5 signals doesn't mean you have 5 carbons. You could actually have 6 carbons where 2 carbons are exactly the same, right? So that kind of a thing you can do with carbon 13 NMRs. A lot of times you need something else also to help you with the carbon 13 NMR, like proton or IR or something like that. But sometimes you can figure out the structures yourself also, okay? With a simple molecular formula, simple NMR, you can do it. So here are some problems you can kind of go through, for solving simple NMRs. And so you can send me the answers if you want, and I can let you know if you are doing okay or not. So here's C5H11BR. Actually, I have 3 spectra, 2 over here and 1 on the next slide. All of them with the same molecular formula, so which means that they're all constitutional isomers. So all you have to do is figure out which isomer we are dealing with. So this one, C5, if you look at the spectrum, you only have 4 peaks in here, but the molecular formula tells you you have 5 carbons, which means 2 of them are alike. Okay, and look at this peak. Oh my God, it's just shooting up there. And so therefore this must be 2 carbons here, that 2CH3s that are alike. Okay, so you can figure that out. So TMS, ignore that, and this is CdCl3. So the carbon of the solvent is showing up here. Okay, so ignore that also. Anyway, so solve this one. Again, this one has 4, and see, this is also giving you the depth. Okay, so CH3, CH2, CH2, CH. So that is just kind of the labeling of the depth NMR for you. So you get an idea that, okay, I have a quaternary carbon in C5H11BR. Okay, so that will help you to determine your structure. And here is the third one. Okay, so figure this out, email me, let me know the structures. And I think that's all we have for carbon 13 NMR.